The next talk is by Indra Dasgupta from IACS, the Indian Association for the Cultivation of Science.
So good morning and good afternoon and good evening from people from various time zones. So I'm going to talk about density functional study of chromium iodide and its implications for neutrons. Well, so this work was done in collaboration with Arun from University of Toronto and Nandini from Ohio State University. And this work has recently been published, where we have essentially looked at exchange interactions and spin dynamics in honeycomb ferromagnet chromium triiodide. So the targeted questions which possibly we would like to address in this talk: what is the microscopic spin Hamiltonian for chromium iodide? The role of ligand in spin orbit coupling. Is the Kitaev coupling important? What is its sign and magnitude? Can we use high resolution neutron scattering to probe the Kitaev exchange for large values of P? Well, so this is something with which we started with. So I don't think I need this slide because we already had a very good introduction about chromium iodide. But I just like to point out two things. So chromium iodide happens to be a Mott or a Hund insulator. And most interestingly, the ligand strongly hybridized with the chromium ion. So this is one of the important things which you should keep in mind. And the thing is that spin orbit coupling is induced by the ligands. So this is an important thing which we possibly keep in mind as we move along. Well, symmetry allowed exchange interaction has also already been said. We will have Heisenberg interaction, Zaloshinsky-Moria interaction, of course, which is second nearest neighbor, single ion anisotropy, anisotropic Kitaev interaction, and the gamma term, the symmetric off-diagonal exchange interaction. And this happens to be the Hamiltonian for chromium iodide, which we are supposed to determine. Well, why we are excited about it? So this is essentially a cartoon of the spin wave dispersion for a honeycomb layer. Only in the presence of Heisenberg interaction, we'll have Dirac cones, 6 Dirac cones. But if there are terms like Zaloshinsky-Moria interaction or ferromagnetic Kitaev interaction, then a gap opens up at the K point, right? And which has been seen in neutron. And of course, if we have the single ion anisotropy and the gamma term, then the gap opens up at the gamma point, that is the Brillouin zone's center. Well, so there has been effort to understand the neutron data, and I think the first talk already mentioned about it. So there was one attempt from Nandini's group, and where it was the importance ferromagnetic Kitaev term was emphasized. So it was basically argued that ferromagnetic Kitaev is an important parameter which is responsible for opening up the gap at the gamma point. Well, so then there has been other from Feng-Chang Dai's group, which essentially consistently has been telling that DM interaction is the most important interaction to open a gap at the gamma point. And experimental spin gap at the Brillouin zone center happens to be about 0.321 MeV, and at the Brillouin zone corner, it is about 4 MeV. Well, so this is where we got into estimating these parameters using density functional theory. And of course, we are not the first to do that, but we try to do a careful calculation, and that essentially brought about few new features. Of course, the leading scale that we figured out is a strong ferromagnetic nearest neighbor exchange interaction. We got a Kitaev interaction, which is smaller than the nearest neighbor Heisenberg interaction. But most importantly, the Kitaev interaction happens to be antiferromagnetic. Well, so we also have a Zaloshinsky-Moria interaction, single ion anisotropy. And then we also evaluated the interplane exchange interaction. And we find that the nearest neighbor interplane interaction to be antiferromagnetic. And on my right, I show the data that has been obtained from inelastic neutron scattering by fitting the inelastic neutron scattering without the Kitaev and the DM term, right? So to summarize, the nearest neighbor ferromagnetic Heisenberg interaction is the most dominant interaction. Kitaev interaction is found to be antiferromagnetic, and it is probably mediated by the iodine ligands, which promotes the T2G EG super exchange path, right? So, and importantly, we get nearest neighbor interlayer interaction is antiferromagnetic, and this possibly can explain the C-axis antiferromagnetic order in thin layers of chromium iodide. Well, so once we have this model parameters, the next step was to go ahead and calculate the spin wave dispersion. And this spin wave dispersion has been calculated by Arun's group. And this was done only considering the Hamiltonian for a single plane of chromium iodide. And this is the spin wave spectra that has been, this is the spin wave spectra that has been obtained by using DFT results. Well, so what we find that the gap at the Brillouin zone corner to be about 3.5 millielectron volt, and the gap at the Brillouin zone center to be about 0.9 millielectron volt from the DFT estimates. And of course, you can see this compares pretty well with the spin wave spectra obtained from inelastic neutron scattering for a plane. Well, so there are, of course, some subtle differences, and these differences can be fixed by tuning the J1 and J2 by a small amount, right? So the theme is that the spectra matches quite well with the inelastic fit, and particularly the width could be essentially tailored by changing the nearest neighbor ferromagnetic exchange interaction by less than 10%. And of course, the flatness that we see out here that can be repaired by changing the next nearest neighbor exchange interaction. Well, so the important point to note here is the comparison with the inelastic neutron scattering happens to be good with our DFT parameters, but the inelastic neutron scattering could only be fitted with the DM interaction where we really don't need the Kitaev interaction. So this is an important thing, that whether really Kitaev interaction is playing any role out here. Well, to see this effect more pronouncedly, what we have done, we have essentially figured out that the mean field contribution to per bond with Heisenberg and nearest neighbor Kitaev happens to be S square. S square is the value of the spin, nearest neighbor Heisenberg plus 1/3 of the Kitaev. So for example, if we take J1 to be ferromagnetic minus 2.11 and K to be equal to 0, then we can clearly see the fit which agrees with the inelastic neutron scattering. Now, if we bring in the Kitaev term and of course an antiferromagnetic Kitaev term, and in the same time reducing the J1, then we find there is hardly any change even when we crank up the Kitaev parameter to a value of about 1 millielectron volt, where the realistic DFT estimates happens to be about 0.2 millielectron volt. So this essentially tells us that it is difficult to resolve the Heisenberg and the Kitaev ambiguity. Well, so this brings us to the next issue. So what we suggested that in order to understand the presence of the Kitaev term, possibly it will be better to subject the sample to an in-plane magnetic field. The in-plane magnetic field will essentially kill the DM term, and if there is any signature of Kitaev term, that possibly may be reflected if we can do a neutron experiment in the presence of a field. Well, so with our parameters, we figure out that the sample is ferromagnetic at a temperature below with a TC of 40.6 Kelvin, which agrees pretty well with 45 Kelvins, and with at zero field, and moments are found to be perpendicular to the honeycomb plane. And as you apply field, right, and then of course, it takes a transition from a canted state to a fully filled polarized state. And this is the situation where you would like to look up the spin waves. Well, so this is the spin wave dispersion where we have taken the Kitaev term to be equal to 0. And here we can clearly see that since the DM term vanishes, because the field is 0 and the spins are all in the XY plane, as a consequence, the DM term vanishes and the gap closes, right, which is expected. And also what we figure out that the gap at all points for the M point remains sort of identical. So the six-fold rotational symmetry is preserved both for the K, which is the corner, as well as the M points, right, for a field when all the spins are in the plane. Well, so now if we go ahead and include the Kitaev term, right, by changing our Kitaev parameter kappa, then we find that in certain region of the Brillouin zone of the K point, the gap vanishes, but the gap persists, right? And the same is true at the M point. There is essentially a deviation in the gap. So the six-fold rotational symmetry is broken both at the K and the M point. And this is the feature which possibly can be probed by neutron. Well, so what we have shown here is the gap values at the K point and at the M point. And what we figure out that for a value of kappa equal to 0.2, which gives rise to a Kitaev about 0.6, which has been estimated from the DFT result, the splitting between the K point turns out to be 0.36 millielectron volt, and at the M point to be about 0.91 millielectron volt. And this anisotropy is possibly could be probed with a neutron done in field. Well, so this brings us to the conclusions. So we've identified a spin model for chromium iodide. Nearest neighbor exchange interaction is dominant, and it happens to be a ferromagnetic exchange interaction. There is, of course, a DM term, and importantly, antiferromagnetic Kitaev present. And this antiferromagnetic Kitaev is probably due to ligands-induced spin orbit coupling. DM is crucial to open up a gap at the K point, and A and gamma open up a gap at the gamma point. And neutron in a magnetic field may identify antiferromagnetic Kitaev term. Well, thank you for your attention.
Thank you, Indra. Let's for that talk. And let's open it up for just a couple of questions. Okay, I think we will have more discussion as we go along. This is bringing some clarity to the experiment and the theory, both from you and Heyang. Let's move to the last talk before we break. From
there was a question, Nandini, in the chat.
Oh, there is.
Good.
Oh,
There's
sorry.
one question in the chat.
Yeah, sorry, I didn't see that. So yes, a question by Evgeny Bats. How many honeycomb layers do you have in the simulations, and thickness dependence of the exchange parameters?
So we have simply taken a bulk chromium iodide in our simulation. So it has 2 layers, I guess. And we have not done the simulations by increasing the number of layers. So it is the bulk chromium iodide for which all the exchange interactions have been estimated. And then we took a layer to calculate our spin wave dispersion.
Okay.
Yes, for TC and so on, we've also checked in more layers, like with 10 layers, to kind of reproduce some bulk physics. But yeah, so whatever Indra was showing was on the single layer.
Right. Okay, thank you.